I'm doing this next lesson a little differently. Uh, it's basically just going to be a live recording of me playing with this to demonstrate what I believe to be the fractal pattern. Um, this was something that I didn't notice when I obviously first made this, but rather it's something that I found through just playing with it a lot. I played with the simulator a lot and was like, hey, that kind of resembles this, and that resembles that. And then I sort of pieced together, like, this must be how things work. But it never looks exactly like anything you and I would recognize or what scientific theory has found through experimentation. And that led me to conclude that part of the fractal pattern is that nothing is ever the same. And so when you look at like the tools that you have available, these sliders are very clumsy. And so they wouldn't reproduce anything like in real life because everything in real life is like has to function down to a very narrow value, and you have these stacks of everything all interacting with each other. So you're not going to reproduce things as you know them, but you're going to see things and be like, hey, that looks like this, imperfectly, and that looks like that imperfectly. And then after about, I don't know, 20 to 40 times of seeing that kind of stuff, you start going, yeah, okay, that's the fractal pattern. So to start, there is a pattern though. There's definitely like a thing that changes in scale. So let's get rid of auto normalization. Because auto normalization is sort of designed to imitate a process that I don't think happens except under certain circumstances, which is like you have a star or something, and it's constantly pumping out energy, and I think that causes the normalization rate to change around it. Let me see here. So we want to set the field normalization to 0. So this is our starting point. These default values that I came up with are ones that are just interesting, but they're not actually like supposed to be representative of anything. It just happens to be a nice midpoint that does a lot of stuff. But if we drop like our lateral displacement down to like very little, or energy displacement down to very little, we can go ahead and we'll just clear everything and keep it at that. So now what you have is a bunch of energy that just propagates, and it doesn't really do very much. So what does that remind you of, right? And that's going to remind you of something propagating through a vacuum. It's not touching anything, nothing's touching it, it just keeps going. So then as you increase the energy displacement strength, then things start to get a little more wavy and stuff like that. So when the lateral displacement factor is very low, it's basically very pointed. And what you can do is, you have these waves, and for me, I find them actually a little uncomfortable to look at. But if you increase the strength, then you start getting, kind of weird things, which is that they actually sort of push the field to the point where they pull a U-turn and turn around. In this case, what is this? What would I say this reminds me of? Well, if you ignore the actual energy balls, it kind of resembles radio interference or radio frequency stuff. We can bump up the lateral displacement, and you end up getting something else, which, what does that look like? Like it must be something that we're not familiar with, but if you guys said this kind of resembles stuff that's at a quantum level, it would make a lot of sense. So we can kind of see that with these displacement things, and of course the field's already now changed, so everything's sort of stuck. So we can bump up our normalization again. You can kind of see like, okay, this kind of resembles waves, wave propagation, things like that. A high normalization, very high normalization. When you increase the displacement factor, you kind of make it a little more rounded. And when you get this nice rounded shape, it starts to form what we call mass, right? From the earlier lesson. And depending on the field normalization, it basically sets the strength of this stuff. So as the normalization goes up, the strength of these displacements goes down, and you see a simulator limitation here, which is that the displacement range is basically setting the point where things are and where they stop, which may or may not resemble a real life process. So what we can do is increase the normalization until it about hits that. And then you kind of see things form like here. You know, this is something that moves in and out of being a triangle. As we're starting at this sort of fringe where it's barely being held together. And you say, well, what does that resemble? Well, that kind of reminds me of quarks. Quarks come in threes, and they change flavors. So maybe this is what a quark is. And quarks make up protons and presumably neutrons. We can continue to change like things like the displacement amounts. You know, increase the factor. So the factor, you know, when the factor is like a magic value. And this is really worth calling out, is that it doesn't necessarily make sense. But it's there for you to play with and decide whether or not you want to, you know, accept that this is something real or something that's not real. So when you bump that displacement factor up to like 5.7, it basically means energy is entering this system and more energy is coming out sideways than we started with. And it's an interesting observation because it's like, well, the rules of energy conservation says that you shouldn't be able to do that, right? But if I'm recreating things and I only do it under a circumstance where I'm creating energy, what does that say about the universe then? Maybe dark energy is a very much real thing, and we are getting, you know, energy created somehow, or maybe there's a mathematical quirk that allows this energy to get created, but it's not really getting created, which is where I have this theory that, you know, things are subdividing. Things are getting smaller. So when things get smaller, you get more units, more units of energy. Energy is created through just getting more smaller energy, and you're getting smaller with it. So to you, it's you're getting more energy out of it. Another way of looking at it is that you get more entropy, more randomization, more chaos over time. So I'm trying to see if there's a good... Let me just reset everything. So another thing you might notice is that, you know, we start with our basic settings here. We create our mass. And one of the things about increasing the energy strength is that it sort of... Well, here it spins faster. If we increase the lateral displacement, things sort of space out. And of course, you know, this increases the change in pressure effects, I guess. But you know, as you just keep adding more things and you increase the displacement factor, it generally spaces stuff out. You get these blobs, and these blobs become further apart where these energy comes in. And you think about the fact that energy and mass are equivalent. Mass is the loop of energy. And you go, oh, this actually makes a lot of sense, because basically as you were to zoom in, the displacement of the energy would seem to get bigger. So even though I'm only increasing the value, I'm simulating the effects of zooming in, because that's kind of what would happen. Like if you look at like photons, they displace the B field, and they do it at a certain range, which is actually quite large, as it turns out. And if you were to zoom in like under a microscope, that relative range would get bigger. And so you, I guess, get to a point where it becomes too big and becomes nonsense. And that's actually what you can kind of see if you just crank everything up on this, right? So you have massive normalization, you have massive displacement. I also want to call out the top ends of these ranges were also sort of guessed and checked in there. Like there could be even higher stuff. But you know, as you just add stuff to it, it just tends to just space out and whatnot. So here I am, I'm adding more energy to this, and as we add more energy, stuff just spaces out. we have our thing. This kind of resembles a hydrogen atom. If you look at pictures of hydrogen atoms, they look a lot like this. And then you sort of get this, as you keep adding more and more energy, you start to get these weirder, like, sort of pressure effects, which may or may not be what a charged particle is. Could also be this is like how we get volcanoes and other stuff and tectonic plates. If you look at how earthquakes tend to happen, they tend to cluster around like one half of the earth and then the other half. And there's a very interesting thing I saw online where someone was basically predicting the next earthquake and doing this successfully based off of where the prior earthquake had been, indicating that there are in fact patterns to it. So that's essentially it in terms of describing the fractal pattern. There's other very things to consider, like when we look at field normalization, it's really the underlying chaos, and so the underlying chaos at a zoomed out level could be very high for relatively large things, and it might recreate stuff that happened at a quantum level. Another thing that can happen that I haven't elaborated too much on is this field blend rate. So the field blend rate can be thought of like almost entanglement. And what it's modeling is field dominance occurring and the rate that field dominance takes over and things have equal values. So you have, and what I've found is that I increase that value, you get actually different behavior, and there's sort of a sweet spot around 0.2 and 0.3-ish. But if you like turn it off entirely, things then start, you can see that they do look a little different. Where I see field blend rate really matter the most is when you talk about like the formation of planets and stuff like that. It seems like when the blend rate is high, stuff tends to form two particles like this, rotating around each other. In fact, I actually have, let me go and just load that from the gallery. Just load it from the gallery here. There we go, the binary formation. So go ahead and download it. All right, and then we will load it. All right, so this is an example of where change in pressure effects matter, or sorry, field blend rate matters. When it gets high enough, you see this happen. And if you crank it up a little bit, it tends to form, yeah, so it'll start to form and they'll congregate, and then you'll get your two things right here, yeah, your two blobs. If you set it to 0, it'll go back to spacing itself out. There, so now it's a ring again. So I thought that was very interesting. It looks to me like the blobs are similar to like the Earth and the Moon. And like both the Earth and the Moon are, you have the Earth spinning, of course, as it normally does, but then you have the Moon, which is tidally locked. And to me, that it kind of looks tidally locked. I guess I can't really ever say for sure it is. See if it'll go back to doing what it did, or if it's spaced out too evenly. Let's just go ahead and maybe add some energy in here. See if that gets it to do it. Okay, here we go. Crank that back down. All right, so it seems to me almost like they're tidally locked and facing each other. Oh, maybe they need to be higher for this case. I don't necessarily see a pattern with the field blend rate. I would expect it to be, actually, I don't know what I expect it to be. If you think about like, if you think about how energy, like at a quantum scale, the blend rate would probably be like 0. I would imagine, and then, or as you get a little bigger, then you have entanglement effects, and that's where it would be probably extremely high. So where we see entanglement happen, it should be extremely high. And then as you zoom out, then I would expect it to decrease substantially. But I could be wrong. So for the last part of the fractal pattern, I wanted to show the shape that is reoccurring. And so you have energy flowing in, and it kind of hits a pinch point, and you get this vortex that forms. It might be spinning this direction, it might be spinning the other direction. It doesn't matter. As you add energy, we saw that things tend to tighten, so the energy then gets tighter and tighter. And this keeps happening until it eventually gets to a point where it runs out of space. And so you're probably familiar with like a black hole, right? Like you think about a galaxy, this is kind of what a galaxy is. And in the interior of it, there's this theory that there's a black hole in the galaxy. But we don't see that anywhere else, right? So with this shape, what happens when this energy gets too tight? Well, you have the carrying capacity kicks in, and that energy gets ejected. So it'll get ejected in like all directions, you know, around here. And if you look at a galaxy, you have an active galactic nuclei. That's essentially why they're all lit up. But then you also have this interior portion, which also gets too tight. And so where does that energy go? Well, in 3 dimensions, it goes straight up and it goes straight down. So I'm going to go ahead and just clear this and kind of draw it from another angle. So the shape that you see that gets repeated is that you get, you know, your spinning vortex, and then you have energy that gets sucked up, and you have energy that gets sucked down. And then there's a bunch of energy that just kind of radiates from the center as well, from this ring, if you will. This maybe you're starting to catch on that, like, okay, if that's the direction it goes, which by the way, we've observed this, so this isn't just theory, we've definitely seen it. What about it? Well, this energy, let me switch to a different color here, that gets ejected is going to have an spin imparted on it. All right, so there's going to be a spin in this direction, and then this one going the other way, which I'll label red, is going to have spin going like this. Okay, so even though they're both originating from something spinning in the same direction, one is going up and one is going down. And if you go look at a map, you will notice that you have north, south, east, and west. But if you go underneath a crane, they a lot of times put a sticker, and the sticker says north, south, east, and west. So these are actually, these corkscrews being ejected are going in opposite directions. And so this should start to resemble, hopefully you're recognizing this resembles the polarity of a magnet, right? And so if you think about it, this energy is getting injected. It's getting ejected into a medium, and it only gets ejected so far before it starts to disperse, and that spin creates the dispersions. So then this stuff's going to come back. This stuff's going to start coming back. And if you look at like energy tunnels, you notice that when things are pointed in opposite directions from each other, they tend to get pulled in. So as a result, you have these things, they come together and they merge, and you have your magnetic field. So then you think about like, well, okay, but our planet isn't a disk, it's a planet, right? So imagine you got energy pushed this way, you got energy being pushed this way, and it gets pulled in. And you just imagine like a bunch of this stuff forming and forming and forming, and it congregates, and then eventually you get yourself a nice little ball. And then you have energy propagating through it, and your ball has a spin to it, so the Earth spins, right? Interestingly enough, there is kind of a counter axis that sort of just naturally forms, and I've demonstrated that in another video, very subtly. So then that explains why there's a tilt that sort of forms on it. It's almost like a mathematical quirk, the mixing angle of the electroweak theory. And so you got this ball, and you have your magnetic field. And if you think about things in terms of like how the quantum world thinks of things, which is to say that there's actually giant gaps in space between atoms, then your very solid Earth is actually more like the dots on a newspaper print, where like when you go to see like them color in the Sunday comics, there's actually just little dots there, and you zoom out enough, it looks solid, but you zoom in enough, you see the gaps. So then in aggregate, you got this magnetic field that's like preserved from the very beginning, and it's still there, and all its energy is just flowing through, and that's how you have your planet with its magnetic field. And so this image isn't mine, but you can kind of see here's the shape, there's the jets. This one apparently has a tail to it, so everything's sort of somewhat asymmetric. But you can see the disk forming, you can see the outflow off in all the different directions. And so you can just imagine the universe is just basically made of this shape at different scales, all coming together. This is the early on thing, and then as energy keeps adding, it starts to become more spherical in the places that actually support it. And then the jets kind of create a polarity. And if you think about how the field is modeled in the simulator, it actually does kind of resemble like there being an intrinsic underlying polarity spread out throughout it. And we can see this shape, at this site here, hosted by uni.edu. Here they talk about a galaxy, and they call the injections of the lobes. You can see a side view of a galaxy here. You can see the evidence of the jets, and you can see the effects of energy through the medium of space. Like, it's not a straight line, right? It actually moves and turns because the medium of space and vacuum itself is not perfectly empty, not perfectly structured. When you can see, like, here's the shape, right? This is it. This is the little magic thing that happens. I would encourage you to look at the universe not in terms of atoms, but in terms of energy. I do that intentionally because I'm just not really sure. Because I see the potential for stuff to happen that doesn't happen at an atomic level. So when they say that, like, oh, here's a dust cloud in space, they actually might be looking at something that's more like, here's the shape of the vacuum itself. So I keep saying that I'm done, and then I remember something else that is kind of important. So in this case, let's go take a look at like gravity, right? Gravitational effects, mass, and everything. One thing that's not really resolved is that there is known atomic forces, and the question is, how does that fit into all this? Because if you look at particle physics, it's not obvious that it fits into this pattern. Well, it turns out that like you can reproduce the strong atomic force with this because of the change in pressure effects. So there's kind of a wall here where stuff's getting repulsed. And for lack of a better term, that wall is kind of like an event horizon. So you're kind of reproducing the theoretical black hole, which may or may not exist, on top of having like this repulsory force as you attempt to enter it. So if we try to go in, we can turn around or get stuck. And if you just kind of add things around the edges, it tends to get stuck there. And that's very reminiscent of the asteroid belt that surrounds the sun, All right, you have this area where stuff sort of congregates. So once you're past that point, you might get repulsed, or if you get close enough, you get pulled in. So you have this sort of middle ground where if you're here, you get pulled in, you get here, you get pushed back. So you have both atomic forces, the strong force and the weak force, being presented here.